All right, let's dive into something truly groundbreaking today. Just when you think smartphones have hit their peak, that they can't possibly get any faster or any smarter, something new comes along that just completely shifts the game.
Hmm.
Today we're talking about a radical reimagining of mobile processing power. And it's all centered around the forthcoming iPhone 18 and its rumored A20 chip.
Yeah, and what's really fascinating here, I think, is that this isn't just another incremental upgrade, not just, 10% faster here or there. It seems to represent a really fundamental shift in how we design and build mobile chips, pushing the boundaries of what's possible on a device you carry right in your pocket.
That's exactly it. That's what caught my eye.
Yeah.
So our mission today is to unpack two really groundbreaking advancements at the heart of this A20 chip. First, there's TSMC's cutting-edge 2-nanometer fabrication process. And second, maybe even more critically, this innovative packaging technology called Wafer-Level Multichip Module, or WMCm.
Right, WMCm.
We want to explore how these advancements aren't just about raw speed, though obviously that's part of it, but they're also about revolutionizing power efficiency, thermal management, and especially the capabilities of on-device Apple Intelligence.
And doing it all while sort of reinforcing Apple's big push on privacy-centric AI.
Exactly. So if these are the core components, what does this all mean for you?
Well, the iPhone 18, which we're expecting around 2026, right? It's definitely generating a lot of buzz. The A20 chip is rumored to be the foundation for the iPhone 18 Pro, the Pro Max, and maybe even Apple's first foldable iPhone, potentially.
Foldable. Wow. Okay.
Yeah, and when we say radical reimagining, we really mean it. It's not just marketing fluff.
It sounds like more than just the next step up. You're saying this chip combines TSMC's bleeding-edge 2-nanometer process with a totally new way of integrating RAM.
That's the core of it, yes.
Okay, but hang on. We've heard about Moore's Law for years, right? This idea that transistors just keep getting smaller and more numerous. Are we actually hitting some kind of wall where just shrinking things isn't enough anymore? Is that why this advanced packaging stuff like WMCm suddenly matters so much?
That's a really critical question. And yeah, you've basically nailed the core challenge. The semiconductor industry is facing real physical and economic limits to traditional silicon scaling, the heart of Moore's Law. Think of it like trying to build higher and higher skyscrapers on the same tiny plot of land. Eventually, it gets incredibly difficult or just too expensive.
Right.
So that's why advanced packaging technologies have become, well, indispensable, absolutely critical. The industry's shifting away from these big monolithic system on chips where everything's baked onto one piece of silicon towards more modular multi-die assemblies, little specialized chiplets working together.
Okay.
And the shift is really pronounced in high-end mobile, like we're talking about, and also in high-performance computing, especially for AI workloads.
So Apple adopting 2-nanometer in this WMCm thing, it's not just them keeping up. It sounds more like you're actively shaping the trend, maybe even setting a new standard for premium phones.
Precisely. I think that's the right way to look at it. What Apple's doing here, it's not just about making phones faster in the old way, it's a statement. It's saying that the old method, just shrinking transistors, isn't enough anymore to meet the demands of modern computing, especially with AI. They're basically telling the industry, look, this is the new frontier. Advanced packaging is essential. And yeah, this move is expected to accelerate the whole industry's transition towards these more complex, integrated solutions. It really highlights how packaging is now just as important as the silicon process node itself.
It's a huge shift in thinking. Okay, so we've established why this advanced packaging is suddenly so critical and how Apple's kind of leading the charge. But let's get specific. For the listener, what exactly is this wafer-level multi-chip module, WMCm, that's causing all the excitement? How does it actually work?
Right, WMCm. It's an advanced chip packaging tech from TSMC, and it's, well, pretty ingenious. It basically allows them to integrate multiple different chip components. Think the CPU, the GPU, the RAM, specifically DRAM, and the neural engine, all directly onto a single wafer.
Onto the wafer.
Yeah.
So before they even cut the wafer into individual chips, they're putting all these different pieces together.
Exactly. That's the key innovation.
That sounds like it streamlines things a lot, maybe removes a whole layer of complexity compared to how they used to do it.
You got it. It eliminates the traditional need for a separate silicon interposer or substrate. Think of an interposer like a tiny circuit board that used to sit between the main chip and maybe the memory, acting as a bridge.
Okay.
WMCm essentially builds those connections directly into the chip's foundation, the wafer itself. This makes communication pathways shorter, faster, more direct. It cuts out that middleman, basically. And this direct-to-wafer approach gives them more flexibility in how they arrange the different chips. They can stack them vertically, place them side by side, optimizing those pathways even more.
Okay, that's a fundamental change. Now, Apple has used advanced packaging before, right? Like, I remember hearing about info in chips like the A17 Pro.
Yeah.
How is WMCm different? What's the key distinction for us, maybe, as users?
Yeah, good point. Apple previously used INFO, that stands for integrated fan-out. We saw it in the A17 Pro, A18 chips. And INFO was innovative, no doubt, but it was primarily focused on, let's say, single die packaging. Often memory was attached right on top of or very close to that single main system on chip. It was really about making that one chip smaller and better performing.
Ah, okay. So info is about optimizing a single monolithic chip.
Yeah.
But WMCm sounds like it's about bringing multiple separate chips, CPU, GPU, RAM together into one super efficient cohesive unit, almost like building a tiny custom computer on one base.
That's a great way to put it. That's the core difference. WMCM excels at integrating these multiple distinct chips within the same package. It lets Apple essentially mix and match different specialized dies, CPU, GPU, neural engine, memory, creating these really complex, tightly integrated systems tailored for specific tasks.
Right.
It represents a big strategic embrace of what the industry calls heterogeneous integration, combining different types of chips, and a move towards a more modular multi-die architecture. This aligns perfectly with where the industry has to go, away from those giant monolithic socks, especially because of the huge demands of modern AI. It's really a pivotal architectural shift for Apple's mobile chips, allows for way more scalability and specialization.
And TSMC's role in this, it seems absolutely central. We know the A20 will be Apple's first using TSMC's 2-nanometer process. Manufacturing starts late 2025. Apple gets first dibs. But it sounds like the partnership goes deeper than just Apple being a customer buying wafers, right? What's the significance of TSMC's specific investment here?
Oh, it's much deeper. Get this. TSMC has established a dedicated production line specifically for Apple's WMCM packaging. It's at their Chi P1 fab, and mass production is expected in 2026.
A dedicated line, just for Apple's WMCM.
Yeah. It signals a really deep strategic interdependence, almost inseparable. The projected capacity is starting at maybe 10,000 units a month in 2026, but ramping up massively, maybe 120,000 units a month by the end of 2027.
Wow.
And here's the really remarkable part. The equipment and processes they're using for this WMCM line are similar to TSMC's CoWoS-L technology.
CoWoS-L. Okay, for those of us not steeped in semiconductor acronyms,
Mm-hmm.
what is that, and why is it a big deal that Apple's getting something similar from mobile chips?
Right, sorry. CoWoS-L chip on wafer on substrate, the L variant, is basically the absolute top-tier packaging technology. It's typically reserved for the most powerful chips on the planet. Think massive GPUs and AI servers, supercomputers and data centers, stuff that takes up racks, not pockets.
So server-grade tech in an iPhone.
Pretty much. The fact that Apple is bringing this kind of high-performance computing packaging tech, something previously unthinkable for a phone, down to a device that fits in your hand, it's genuinely mind-blowing. It really signals that WMCM, or approaches like it, are going to be foundational for the next wave of high-end mobile devices. It underscores again that advanced packaging is now just as crucial as shrinking the transistors themselves. TSMC wouldn't build a dedicated line like this unless they and Apple were extremely confident in WMCM long-term.
That is wild to think about. Okay, let's pivot to the real-world impact then. How will this WMCM technology actually transform the iPhone 18's performance and efficiency for us, the users? I'm hearing that directly integrating the RAM onto the same wafer drastically cuts down the distance data needs to travel. Less distance, less delay, faster access.
That's exactly right, and it translates into very tangible benefits. Shorter distance means less latency. Data moves between the processing unit, CPU, GPU, and the memory much, much faster. It's like upgrading from local roads with traffic lights to a direct high-speed tunnel. Initial projections, and these are just projections, suggest A20 chips could be maybe up to 15% faster than their A19 predecessors. But honestly, the story isn't just about peak speed.
Right, because usually faster means hotter and drains the battery quicker. But you mentioned efficiency improvements earlier, too. How do they achieve both faster and more efficient?
It's that synergy we talked about. It's the combination. First, you have the 2-nanometer process itself. Smaller transistors inherently use less power for the same operation. Then WMCM's direct integration helps significantly. Because data travels shorter distances, it requires less electrical power just to push the signal around.
Okay. Less effort to move the data.
Exactly. So the A20 chips are anticipated to be maybe up to 30% more power efficient than the A19 chips. Less power needed means longer battery life for the iPhone 18, and that's always a huge win for mobile users.
Definitely. Okay, what about heat? We've all felt phones get uncomfortably warm, especially during gaming or heavy tasks. These super dense chips must generate a lot of heat. Does WMCm help manage that?
It does, yeah, that's another key benefit. Because WMCM allows for a more compact and optimized layout within the chip package, it actually improves heat dissipation. Think of it like designing a car engine with better internal cooling channels. Heat can escape more efficiently from the hotspots.
So it runs cooler, or at least manages heat better.
It allows the A20 chip to maintain its peak performance for longer periods without having to throttle down, which is that annoying slowdown you get when a phone overheats. This is absolutely crucial for demanding stuff like high-end mobile gaming or those intensive AI workloads we keep mentioning.
And any other knock-on effects. Maybe space saving.
Potentially, yeah. The smaller overall package footprint could free up some precious internal space inside the iPhone. Apple could use that for, say, a slightly larger battery or perhaps more advanced camera components. Always a balancing act inside these devices.
Makes sense. And what about the RAM amount itself? There are rumors, I think, from analyst Ming-Chi Kuo suggesting the iPhone 18 Pro models could jump to 12 GB of RAM. That's up from 8 GB currently. Is WMCM enabling that increase?
It seems directly linked, yes. The ability to efficiently integrate more memory modules right there on the wafer, super close to the CPU and neural engine, is a direct capability of WMCM. And bumping up to 12 GB of RAM, that provides a significantly larger workspace for complex apps, multitasking, and especially for holding the large data sets needed by those advanced on-device AI models. Everything should feel smoother.
So it really isn't just one single thing making the A20 chip better. It sounds like this powerful synergy. You've got the 2-nanometer process giving you denser, faster, more efficient cores. Then WMCM removes that critical bottleneck of accessing memory, letting those cores really stretch their legs and run at peak speed for longer. And then the potential boost to 12 GB RAM just amplifies everything, especially for AI. It feels like a much more profound leap than just tweaking one aspect.
I think that's exactly right. It's a comprehensive approach. This level of deep hardware-software co-optimization, it's really a hallmark of Apple's strategy, isn't it? They design the silicon specifically to enable the software experiences they want to deliver. They're building the whole system, foundation to ceiling.
Okay, given all these gains, faster speed, better efficiency, improved thermals, more RAM access, it sounds tailor-made for Apple's big push into on-device AI. How does WMCM specifically supercharge what they call Apple Intelligence? What does it mean for the neural engine, for instance?
Well, AI and machine learning models, especially the really sophisticated ones like large language models, they're incredibly hungry for two things: raw processing power and super fast access to data, lots of data. The reduced latency and faster data access you get with WMCM, that directly translates into quicker execution for these complex AI algorithms. Less waiting around for data.
Right.
Think about the neural engine, Apple's dedicated AI processor. It's already a beast, capable of, 35 trillion operations per second in the current chips. WMCM basically gives that AI brain a direct, high-speed hotline to the memory it needs. This lets it run much more efficiently, especially for demanding on-device tasks. Things like real-time image analysis, understanding natural language, complex computational photography. All that stuff gets a significant boost.
And this ties directly into Apple's whole strategy around Apple Intelligence, focusing on privacy, keeping computations on the device itself, right?
Absolutely. That seems to be the core strategic driver here. Apple's approach emphasizes integrating powerful AI, even generative AI, directly into apps, but with a huge focus on user privacy by doing as much processing as possible on the device. WMCM's ability to enable faster, more efficient on-device processing is key. It minimizes the need to constantly send your data off to cloud servers.
Less data leaving the phone means less risk of privacy breaches.
Exactly. And the performance and efficiency gains from WMCM are what make it feasible to run these quite complex multi-billion parameter AI models like Apple's foundation models locally on your iPhone. If the chip was slower or less power efficient or generated too much heat trying to run these models locally, the whole on-device strategy would fall apart. WMCM makes it practical.
So WMCM isn't just a nice-to-have performance bump. It's actually a foundational piece enabling Apple to execute these complex AI models efficiently right there on the iPhone. This deep hardware-software integration, it sounds central to their unique privacy-first AI approach gives them a real competitive edge, maybe?
I think that's the key takeaway, yes. It's what potentially allows Apple to differentiate their AI. They can offer powerful features and strong privacy assurances. That's a combination that's really difficult for competitors to match if they don't have the same level of tight integration between the silicon design and the software strategy.
Okay, let's zoom out for a second. Where does WMCm fit in the bigger picture, the broader semiconductor landscape? We hear terms like 2.5D integration, 3D stacking, chiplets. Is WMCm part of that general trend, or is Apple kind of doing its own thing here?
No, it's definitely a significant development within that broader industry trend towards advanced packaging. All these techniques, 2.5D, 3D stacking, multi-die assemblies like chiplets, and now WMCm, they're becoming really key differentiators. They offer higher performance, more design flexibility, potentially faster time to market, especially for high-end mobile and high-performance computing. It's like the industry is moving from designing single, giant, do-everything buildings to creating complex, interconnected cities with specialized districts, if that analogy helps.
Yeah, that makes sense. So while the traditional all-in-one chip, the monolithic SUS, might still be fine for cheaper phones, these multi-die approaches have big advantages at the high end. What are those advantages beyond just performance?
Well, a few key things. First, the ability to incorporate diverse compute elements. Maybe you want a cutting-edge CPU core, but also a specialized AI accelerator built on a slightly older, cheaper process node. Multi-die lets you mix and match. Second, flexibility. You can integrate components optimized for different things without having to design one massive, complex die that does everything okay, but nothing perfectly. Third, bandwidth and power efficiency. Connecting these specialized dies closely can actually be more efficient than trying to wire up a giant monolithic chip, and potentially cost. As making huge, cutting-edge monolithic chips gets insanely expensive, assembling smaller, proven chiplets might become more economical for complex design.
Okay, so Apple using WMCM for iPhones. It mirrors what's happening in servers and high-performance computing. It's like a convergence of strategies.
Exactly. It signals a clear convergence. The design philosophies for the most powerful computers and the most advanced smartphones are starting to look increasingly similar, at least architecturally. The fact that Apple's embracing a packaging tech like WMCM, which, as we said, shares DNA with server-grade tech like CoSL, it really underscores that advanced packaging is now seen as the main path forward to overcome those traditional silicon scaling limits across the board.
And it's not just Apple and TSMC pushing this, right?
Yeah.
Are other big players, research groups involved in driving packaging innovation? Is this a widespread effort?
Yes. Oh, absolutely. It's a huge area of focus globally. Leading research institutions like eLookin in Europe, they're doing pivotal work on 3D integration, figuring out how to stack chips effectively. In the US, you have groups like the Semiconductor Research Corporation funding university research specifically on heterogeneous integration and packaging. They have a center called CHIPE. And major industry players are all investing heavily. Intel, for example, has its own advanced packaging technologies like EMIB and Foveros, which they're using for their high-end CPUs and AI processors. So yes, this widespread investment from academia and industry really validates how crucial advanced packaging has become. It's where a lot of the innovation is happening now.
Right. So looking ahead then, what are the big strategic implications for Apple Silicon with the A20 chip and WMCM leading the way? It feels like this is just going to cement Apple's lead in mobile chip performance and efficiency.
It certainly looks that way. The A20, combining 2nm and WMCm, is expected to set new benchmarks for the entire industry, and it strongly reinforces Apple's core strategy: vertical integration, tight control over hardware and software, optimizing them together. This creates that seamless user experience that's historically been very, very difficult for competitors relying on off-the-shelf components to replicate. It's their secret sauce, and WMCm makes it even more potent.
Now, this WMCM tech sounds incredibly powerful. Could we see it migrate beyond the iPhone? What about Apple's M-series chips for Macs and iPads? Any potential there?
That's a really interesting question, and analysts are definitely speculating about that. The thinking is if WMCM proves successful and scalable in the A20, it could be a genuine game changer for the M-series chips down the line, potentially debuting in, say, the M6 series around 2026 or so.
A game changer how? What could it enable for Macs?
Well, currently, for their most powerful chips like the M Ultra series, Apple essentially stitches two Max dies together using their UltraFusion interconnect. WMCM could potentially offer a more elegant, perhaps more efficient way to build extremely powerful multi-die processors. It might allow for integrating much beefier GPUs or a significantly more memory bandwidth, or even offer unprecedented flexibility to, as we said, mix and match different specialized dies. You could see Apple creating a wider, more tailored range of M-series configurations for different iPads and MacBooks, hitting specific performance and efficiency targets more precisely than ever before.
Hmm. That opens up a lot of possibilities. But okay, let's bring it back down to earth. Adopting this kind of bleeding-edge tech, especially for a mass-market product like the iPhone, must come with challenges, right? What are the potential hurdles?
Oh, absolutely. Cost is a big one. Both the 2 mm process and this advanced WMCm packaging are incredibly expensive, especially initially. That's likely why the rumors suggest only the iPhone 18 Pro models will get the A20 chip with 2 mm WMCm at first. It seems like a deliberate strategy from Apple. Create a more pronounced performance gap between the standard and Pro iPhones, drive more users towards the higher margin Pro models.
Makes sense from a business perspective. What else?
Thermal management, while improved within the package by WMCm, remains a persistent challenge overall, cramming ever more powerful chips into thin phone bodies. Dissipating that heat effectively is a constant engineering battle. Sustaining peak performance without throttling will always require clever cooling solutions outside the chip, too, within the phone's design. And finally, there's always supply chain dependency. Relying so heavily on a single foundry partner, TSMC, even with a deep partnership, introduces inherent risks. Although Apple's scale and influence certainly help mitigate those risks better than most.
Right, so costs, thermals, supply chain. But the opportunities, particularly around AI, seem pretty significant in the long run.
Absolutely. The potential payoff is huge. The enhanced on-device AI capabilities unlocked by WMCm and the A20 create massive opportunities for Apple to expand its software ecosystem. Think about new kinds of AI-powered apps and features that truly leverage that local processing power while prioritizing user privacy. That aligns perfectly with Apple's brand and values. That's likely where they see the biggest long-term strategic advantage.
Okay, so let's try and wrap this up. To recap, the iPhone 18's rumored A20 chip, powered by TSMC's 2 nm process and this really revolutionary WMCm packaging. It genuinely marks a pivotal moment, a potential inflection point in mobile silicon design. We're talking not just faster speeds, but fundamental enhancements in performance, power efficiency, thermal management, and critically enabling Apple's whole strategic vision for powerful, private, on-device Apple intelligence.
Exactly. By fully embracing this heterogeneous integration, this multi-die approach with WMCM, Apple isn't just keeping pace. They seem to be actively setting new benchmarks for what's possible in these compact, high-performance mobile devices. And the ripple effects could go far beyond the iPhone, potentially transforming their M-series chips for Macs and iPads and really solidifying their competitive edge across the entire semiconductor landscape for years to come.
So here's something to think about as we finish up. We see this incredibly powerful new hardware coming, specifically designed to enable sophisticated on-device AI with a major focus on privacy. What does this truly mean for how you will interact with your phone, your tablet, your computer in the next few years? How might this shift change your own expectations, your balance between personal privacy and the convenience of cloud-based intelligence in the apps and services you use every single day? Something to ponder.